A random variable is a function from a sample space into the real numbers. This is a sample space. And here in this sample space, we have defined a probability. That means that it makes sense to talk about the probability of an event. And this number is a number between 0 and 1. When we have a random variable, it makes sense to talk about the probability that x is in a particular set of the real numbers, or subset of the real numbers. For example, it makes sense to talk about the probability that x is between a and b. And then essentially what we need to do, here is our sample space omega, and here is the real numbers. Then here is the set b. Then we need to solve this equation. Think about what elements in omega goes into b, and this event e is a subset of omega. Then the probability of e is what we define as the probability of x being an element in b. And then we can assign a number to this. Somehow, we are going to forget about the sample space. We're going to forget about the sample space, and we're going to provide a way to define this number. And the way we're going to do it is we're going to use a positive function, f of x, sorry, not positive, but bigger or equal than 0 function. And we're going to define this as the integral from a to b of f of x dx. Since we want the probability that the random variable goes from negative infinity to infinity, clearly this is going to be just the probability of the whole sample space. Then we want this to be 1. Then one of the conditions that we want from this function is that the integral from negative infinity to infinity of f of x dx is equal to 1. We're going to call this function the probability density function. Once we have the probability density function, then we can compute the probability of most of the subsets of R, and we can also compute the expected value of the random variable. The expected value is going to be just the integral from negative infinity to infinity of x times f of x dx, and we're going to denote this by mu. And we can also compute the variance of x, and this is just the integral from negative infinity to infinity of x minus mu squared times f of x dx. And we can also compute the standard deviation to be the square root of the variance. Notice that to define a continuous random variable, the only thing that we need is a probability density function, which means we need a function that is not negative, that we can integrate, not necessarily explicitly, and that it has this property. That function doesn't have to be continuous. Let me give you a first example. Let's suppose that our function is defined in the following way. Before 0 is 0, after 5 is 0, and between 0 and 5 is given by f of x equal to 1/5, right? That happens if x is between 0 and 5 and is 0 everywhere else. Then let's compute the probability that x is between negative infinity and infinity. This is supposed to be 1. Is the integral from negative infinity to infinity of f of x dx. But this function is defined in pieces. Then I should do the integral from negative infinity into 0 of the function plus the integral from 0 to 5 of the same function plus the integral from 5 to infinity of f of x dx. And this is just the function before 0 is 0. That means that this integral is 0. This part here is 0. And this is just the integral from 0 to 5. The function between 0 and 5 is 1/5 dx. And this is just 1/5 of x from 0 to 5. And this is 5 minus 0 over 5, which is just 1. Then, as expected, this probability is equal to 1. But we can do more things with this. I can compute the probability that x is bigger or equal than 4. Then this probability is the integral from 4 to infinity of f of x dx. But then you divide the integral in as many pieces as the function is defined. Then you integrate from 4 to 5, because there is a splitting in the definition of 5 of the function of f of x dx, plus the integral from 5 to infinity of f of x dx. And this is just the integral from 4 to 5 of 1/5 dx. This function between 4 and 5 is given by 1/5, plus the integral from 5 to infinity of 0 dx. This part is 0, and this is just 1/5 of x between x equal 4 and x equal 5, and this is just 1 minus 4/5, which is 1/5. Then this probability is 1/5. Let's do, for the same example, we're working with this example here. Let's compute the expected value, the variance, and the standard deviation. For the expected value, is just the integral from negative infinity to infinity of x, f of x dx, and this is equal to the integral from negative infinity to 0 of f of x dx, plus the integral from 0 to 5 of x, f of x dx, the integral from 5 to infinity of x, f of x dx. These two parts are 0 because the function before 0 and after 5 are equal to 0, and the function between 0 and 5 is 1/5. Then I end up with the integral from 0 to 5 of x times 1/5 dx, and this is 1/2 times x squared times 1/5 between 0 and 5, and this is essentially x squared over 10. Then is 25 over 10 minus 0, and this is just 5/2. This is the expected value. let's compute the variance. To compute the variance of x, we need to do the integral from negative infinity to infinity of x minus 5/2 square of f of x dx. And same reasoning, you end up with just the integral from 0 to 5, because the other two integrals are equal to 0, of f of x is 1/5. And here we get x minus 5/2 square dx. And this is the integral from 0 to 5 of 1/5 times x squared minus 5x plus 25/4 dx. And this is 115 times x cubed. The integral of x squared is x cubed over 3, x cubed minus, here these two 5 cancel out, the antiderivative of x is x squared over 2 plus 25 plus 5/4. These 25 and 5 cancel out, and then 5/4x between 0 and 5. And then I end up with 125/15 minus 25/2 plus 25/4 minus 0. And this is equal to 25/12. And then the standard deviation is going to be the square root of 25/12, which is approximately equal to 1.4438.